Okay, let's jump right into this explainer and see what happens when pristine materials, perfectly engineered in a laboratory, meet the completely unpredictable reality of a live construction site. We spend so much time marveling at the incredible properties of modern building materials, but let's be real for a second. There is a massive gap between a tightly controlled lab test and a chaotic real-world application. Today, we're bridging that gap. We'll explore the exact science behind these materials, and then we'll see how everyday site conditions can completely unravel that brilliant science if you aren't paying close attention.
Think about it. A multi-million-dollar engineering spec sheet literally means nothing if we don't understand how these materials actually react once they're exposed to the elements. In the laboratory, you have a world of controlled variables, precise measurements, and absolutely perfect ambient temperatures. But out on the job site, you're dealing with wildly swinging temperatures, rough handling, and constant environmental exposure. The contrast is just staggering. Our goal today is to really understand how materials survive that transition and what you need to look out for to ensure a structure doesn't fail before it's even finished.
Section 1. Cement, water, and hydration.
Cement is the absolute glue of our modern world, but its strength relies entirely on time and moisture. When you add water, a chemical reaction called hydration kicks off, moving the mix from an initial workable stiffness to a final solid state. But here's a massive reality check. The most expensive, high-grade cement in the world is effectively useless if it absorbs moisture from the ground before it ever hits the mixer. Storage matters. If you're leaving bags directly on a damp floor instead of up on a wooden pallet, your setting time is ruined before you even start pouring.
Now, in the perfect conditions of a lab, we use a highly precise 3-step Vickett apparatus test with a specialized needle to measure setting times down to the minute. It's incredibly exact. But out in the mud of a real site, we rely on simple practical audits, like the finger test. Literally just feeling for hard clumps in the bag. If you find them, it tells a project manager immediately that moisture has already compromised the batch.
And when it comes to mixing, the water-to-cement ratio is absolutely crucial. Adding extra water just to quote-unquote ease the flow is the #1 way to destroy a high-strength concrete mix. To check this on site without lab equipment, we do the bucket drop, essentially a concrete slump test, to see how much the wet mix actually sags. Plus, the environment is constantly fighting the engineering. High ambient heat acts like a catalyst, rapidly speeding up hydration, while a freezing morning will severely delay it.
Moving on to Section 2, Visualizing the Invisible, Steel Rebar.
So, how do you know what kind of literal steel backbone you're working with when it's just lying there in the dirt? Well, you don't need a microscope, you just need your eyes. A green painted end, or a single continuous line running right between the outside ribs, instantly confirms that you're holding high-capacity grade 60 rebar, capable of withstanding 60,000 psi. It's a brilliant, simple visual audit.
But the steel grade is only half the story. When freshly delivered, steel is covered in a bluish-black, flaky coating called mill scale. This is actually a complex mix of iron oxides created by the intense heat at the mill. In theory, this scale acts as a protective shield against atmospheric corrosion. But don't let it fool you, because on a rough job site, it can easily become a ticking time bomb for rust.
See, while perfectly intact mill scale protects the steel, the gritty reality is that just a single deep scratch from a rough handling chain turns that scratch into a literal battery. Because this oxide layer is electrochemically cathodic to the steel underneath, moisture creeps inside that break, and it dramatically accelerates the corrosion of the exposed metal. If you try just painting over broken mill scale, the moisture will literally peel the paint right off from the inside.
Which brings us to Section 3, Bricks and Aggregates.
Let's look at our heavy masonry and structural fill. In the lab, a high-quality extruded shale brick, like this Glengarry sample, can withstand an unbelievable crushing force of over 14,000 psi. The lab data tells us this brick is an absolute powerhouse, easily capable of supporting massive architectural loads. And a great way to check that quality on site? Just tap 2 bricks together. You want to hear a sharp, metallic ring, not a dull thud.
However, here is the catch. If that highly absorptive brick is laid totally dry on site, it acts like a giant sponge. It aggressively sucks the moisture right out of the mortar, completely destroying the chemical bond, no matter how strong the brick itself is. To catch this, smart site managers do a quick water test. You simply weigh a dry brick, soak it in a bucket, and weigh it again to find its absorption rate. If it's too thirsty, those units absolutely must be heavily wetted down before they're ever laid.
And when we're sourcing concrete aggregates, remember that shape matters just as much as size.
High-quality angular rock geometrically locks together under pressure, creating immense compressive strength through that interlock. Cheap, rounded rock just slips and slides. Also, if you're using recycled tunnel rock, the microscopic dust and silt, the fines created by drilling, will totally destroy your concrete's flow. It has to be heavily washed and run through mechanical scalping screeners first.
All right, Section 4, the Site Material Quiz. Let's step into the shoes of a project manager for a second and see how sharp your eyes are.
Here's the scenario. Imagine you're walking a site, and you see a stack of rebar marked with white paint on the ends. Is this suitable for a heavy, load-bearing concrete beam? I'll give you 3 seconds. What do you think?
Absolutely not. That white paint specifically indicates grade 33 steel. Now, that's perfectly fine for a small backyard patio, but you definitely wouldn't want it holding up a heavy structural roof, especially out in earthquake country. Plain carbon steel has its uses, for sure, but heavy structural support is not one of them. Okay, next up, you're inspecting a steel beam and you spot a deep scratch breaking that dark bluish-black mill scale coating we talked about. Is this just harmless wear and tear from transport, or is it a major red flag?
That is a massive red flag. Remember, moisture-laden air will immediately get right under that broken mill scale. It causes protective paint to fail and rust to spread rapidly beneath the surface. That single scratch just created a localized battery that is actively eating away at the integrity of your structural steel.
I highly recommend grabbing a quick screenshot of this quick material quality audit table. It's a great summary. It reminds us to always check cement manufacturing dates and look for those hard clumps. Check your aggregates for cleanliness. Visible mud or silt is a no-go. For steel, look at the rib patterns and watch out for deep pitting or flaking rust. And for bricks, remember to tap them to ensure they have a solid metallic ring, not a dull sound that indicates hitting cracks or excessive breakage.
So, I'll leave you with this final, crucial question. Are the conditions on your job site protecting the brilliant science behind these materials, or are they actively tearing it down? Engineering theory is the pristine foundation of everything we design, but the gritty construction reality determines if it will actually stand the test of time. Thanks for joining me on this explainer. Keep your eyes open out there on the site, and never take a perfect spec sheet for granted.